our calculus notes. We talked about page 1 briefly in class, so let's just start there. Continuity, there are a lot of different definitions. One of the more simple definitions is if you can draw it without picking up your pen, it's continuous. We know that's not exactly the case, so I really like this definition up here, where it's continuous if the function is equal, the function at a is equal to the limit of the function as x approaches a. So, for example, if I look at this part of my function, you could make an argument that if I were to take my pencil, I could draw this function without ever picking up my pencil on this interval. That's a pretty common definition in like an Algebra 2 class. But the problem with the definition of as long as I can draw it without picking up my pencil, it's continuous, is that I have this discontinuity. I have this hole here that tells me that this really isn't continuous. So yes, I could draw it without picking up my pencil, but this is not continuous. I think a better example is the other half here. The limit from the left-hand side as x approaches 5 is the same thing as the right-hand limit as x approaches 5, but because f of 5 is up here, then I know that that's not the true value down here. I know that the limit is not the same as the true value of f of 5, so this is discontinuous. I have a hole. So that's one really good definition. If I were to look at something like this problem, f of x equals x squared minus x minus 2 over x minus 2, well, I can take this and I can factor that and say f of x really equals x minus 2 times x plus 1 over the quantity x minus 2. And I know that when I simplify this, I can simplify this and this. And if I'm trying to calculate the limit of f of x as x approaches some value, it's going to be this, right? And if I were to graph that, it looks like the graph of x plus 1, or y equals x plus 1, because it is essentially that. But the problem is that as I approach 2, I have a hole. It's undefined at 2. So even though the limit as I approach 2 is the same, I'm approaching 3 from the left, I'm approaching 3 from the right, but I get undefined. I get a hole. So this would be undefined at x equals 2. It's discontinuous at x equals 2. So is the limit from the left-hand side a number? Yeah. And I've got the same number as the limit from the right-hand side, but it's discontinuous. There's a hole at 2. So, same idea here. I've got this 1 over x squared and 1. If I were to graph these, let me say negative 1, 0.01, negative 0.01, x 0. Let's make it 2. Let's do that so you can kind of see it. So I've got this function that is 1 over x squared, 1 over x squared, and then I've got the true value at 0 down here because of the piecewise part. So I've got these limits, and these limits agree they're both positive infinity, but f of 0 is 1. right there. So I've got a discontinuity. In this case, f of x is discontinuous at x equals 0. Because f of 0 is not the same as the limit as x approaches 0. All right, let's take a look at our next page. Now, if I were to take that first function and say, okay, so let's do a piecewise. This is piecewise. We know that originally it was discontinuous. It's undefined at x equals 2, so there's a discontinuity there. But if I were to say, okay, just ignore the 2, we're going to say that it's equal to 1. Well, still, even there, the limit is supposed to be 3, but it's still discontinuous at x equals 2 because the limits, where is it? The limit, limit as x approaches 2 of f of x is 3. But f of 2 is 1. So it's discontinuous still. It still doesn't matter. Now I could change that and I could say, okay, well, what if I made that instead of 1, if I made that 3? Basically, if I made this part right here, I made this into a 3, then yeah, we'd be fine because the limits are the same as f of 2. We're just plugging that hole. But unfortunately, it doesn't say 3, it says 1. So, still discontinuous at x equals 2. Our floor function, this is where we round down, looks like this. Our floor function is discontinuous at every single integer, because at every integer I have a jump. So if I were to graph this, this would be fx is discontinuous at all integer values, because at all integer values I've got these jumps at 0, at 1, at 2. I'm jumping up to a new flat line. Okay, our definition 2.5.2 says a function is continuous from the right at a number a if the limit from the right is equal to f of a. And it's continuous from the left if the left-hand limit is equal to f of a. So in what directions is the function continuous? Well, it's continuous from the right because f of 1 is 1 and the limit from the right is 1. Here f of 0 is 0, the limit from the right is 0. So in this case, this would be continuous from the right because the right-hand limits for all integers are equal to the values of f of x for all x in the integers. So where's my symbol? For all x in the set of integers. Oh, there it is. So for all integers, for all x values in the integers, the right-hand limits agree with f of x. Okay, and our function is continuous on an interval if it is continuous at every single number in the interval. So basically what that's saying, if we go back here, I could say that, where'd it go? There we are. I could say that f of x is defined on an interval here if it's continuous at an interval here if I don't have any holes or discontinuities. So if I cut out the discontinuities, I can say that it's defined on it's defined on this interval right here, it's defined on this interval, right? As long as I cut out the discontinuities. So I can kind of cut out the bad parts and still have continuity on some interval. So part 2 of this is going to be looking at continuity on intervals. Check out that video in just a few moments.